Hey guys, welcome back to AlgoYogi. We have started a binary search series. We have solved one of the problems, binary search, and our next problem in the list is search insert position. So let's visit the problem on LeetCode. So given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. And we must write the algorithm of log n time complexity. Now, this problem is exactly like binary search, right? And it's just one minor change is that if we were not finding the element in binary search, we were returning -1. But in this case, they've asked us to return the index where that target would be if it were to be inserted into our given nums. Right now, maybe our nums array has the target, it might not. So first case, you can see 5 is present, then we will return basically 2, that is the index of the target. But in second one, you see that target is 2 and 2 is not present here, but we would not return -1 just like the binary search, but we would return basically 1 because this target 2 will be inserted at the place of 3 will be shifted, 5 will be shifted, or whatsoever, right? So that's why we return 1. So if that index is not present where our target is, then we return basically that index where it will be inserted. Okay, so let's go through our basically approach. Now in the first example, which is from the LeetCode, we're going to, before we move forward to our approach, we should talk about the brute force approach. I guess it's okay. It's good to talk about the brute force approach, which would be in big of n time complexity. Although they have asked us specifically that we have to have a solution of log n, but in this case, like you can talk about for loop where you are basically checking if your current num is equal to target. If it is, then you return the number. Otherwise, you basically keep checking if your current number is basically smaller than your target. If it is, then keep moving forward. And if there is any case where you find out your current number is greater than your 5, that means the previous index was supposed to be returned, right? So I'm sure you can figure that out, but let's move to the binary search approach, which is the main approach that will give us the time complexity big of log n. So from the binary search solution, we know that we're going to have basically our left pointer, which will be basically in the beginning, and then our right pointer, and each time basically we find the mid. And the way you find mid is basically left plus right divided by 2. So in this case, you can see our mid would be 0 plus 3. In this case, you can see target is present in our nums. Then we would return, the index. And I think we will be able to find a condition where my middle index is equal to the value that I'm trying to search, which is the target. So in this case, you can see this returns me 1 is 3. Is 3 equals to 5? No. So that means what? We check if 3 is greater than 5 or 3 is lesser than 5, and based on these two conditions, we decide if we wanna basically start searching our element, our target, in the left half or the right half, right? So this happens to be that this is 3 is smaller than 5. That means my 5 will appear in the next half, right? The right half of the array. So basically this is what I'm talking about. So it should be present over here. In that case, what I'll do is I'll move my left pointer. Basically, in that case, I'll move my left pointer. And let me go back to clear things up. So I'll basically move left pointer to mid plus 1, which would be over here. Okay. Again, the same approach, we'll take to find the mid, and that will be basically 2 plus 2 plus 3 divided by 2, which is 2.5, which is this. This time it will become equal. The index is basically 2, so our answer would be 2. So we'll return 2. Okay, so this was the case where we had target present in our nums. What if it is not? So let's go to the example 2. In this case also, we're trying to find a target. Target is 2. Now let's have our basically left and right pointer. Our indexes are 0, 1, 2, 3. Now let's find the mid. Mid would be 1 in first case. So 0 plus 3 divided by 2 is 1. So if this is the mid, I see that this is not equal to 2, but I know my target is smaller than 3. That means it should occur in the left half, right? It should occur in the left half. So what I'll do is I'll move my right pointer to basically mid minus 1. So what will happen is or by the way, like we'll have the while loop checking if left is smaller than or equal to right, because once these pointers cross each other, we don't want to continue the while loop to search the result. That means it either wasn't present or it was basically we found the location where it should be present. So we'll keep that check, like where left is less than or equal to right. So this will be the condition for our loop. So what's going to happen is, since this is greater than 2, that means I will move my right pointer to mid minus 1. So I will move this pointer to mid is 1, basically 0, right? 0, and then I will check. Then I will find out the mid again. That will be basically left plus right divided by 2, which in this case is 0 plus 0 divided by 2. That would be 0 itself. Is 2 equal to 1? No, in this case it is not. That means what? We're gonna check if where should my target be in respect to my current mid. Current mid is 0 index. The value is 1. So we know that target is greater than 1. That means I need to that it's gonna be present in the next half. Although there is nothing left over here right now, but still, as per the logic, we will move our left pointer basically by 1. So L will become left plus 1. Now L is basically 1. Okay, right is 0. Right is 0. L is 1. This particular condition falsifies. Okay, so this falsifies, and the reason is that now my L is 1. Well, 1 is not less than not less than or equal to 0. Then we will come out of the loop, but my left is pointing to basically 1, and that's what we return. All right, and I think in every case we will return left if we are in a situation where we did not find the element. So we'll come out of the loop based on this condition, and since we know that all the elements lesser than the target will be basically behind, I would say all the indexes that will be less than left, and all the elements greater than target will be greater than right, then we will return basically left will represent the right position for the target to be inserted. I think you get it. Okay, I don't know if there is anything else to talk about here. Let's talk about the time complexity, which will be, so what's happening is each time, let's say this is my input size, and this is my left pointer, this is my right pointer. Every time I try to find basically the mid, and based on that I basically either choose to go to the left half or choose to go to the right half. That means my input becomes half each time. Either this left goes, either I move left to mid plus 1 or right to mid minus 1. And because of that, what's happening is each time my input is basically being brought down to basically half. So initially it was n, then it becomes n minus or n by 2, and then n by 4, or 4 could be written as 2 to the power 2, right? So it's gonna, at one point what will happen is my input size will become 2 to the power n by 2 to the power k equals to 1. Basically at the end I just come to basically when the size of the array is just 1. So in that case what's going to happen is if we basically send 2 to the power k to the right and take log both side, and the base would be 2 by the way, so 2 by the way, so this k will come in front, so k and these two will cancel, k will be equal to log 2 n. So this represents basically the time complexity here. This k represents the number of time we had to repeat this operation, and that is what the time complexity is, guys. So and space would be constant. Okay, so let's write down the solution, and I think it's really clear. Okay, looks all right. As I said, we're going to have left and right pointers. Left will be 0 and right would be length of nums minus 1. And while left is less than or equals to right pointer, then we're going to do is we're going to find mid. Mid would be left plus right divided by 2. And if nums mid is equals to target, that means we want to return mid. Otherwise let's check if my target is greater than, if my target is greater than my mid indexed element, that means what? I need to move my left pointer to mid plus 1. So left will be mid plus 1, else I will move my right to mid minus 1. Okay, mid minus 1. So this is the case where like nums mid must have been greater than target. So target needs to basically lie behind the current numbers, like before current number, not behind. Okay, so now if either we found the number, we returned mid, or we didn't, that means L should be pointing to the position because of this condition. This condition means it only happens, we only come out of this loop when left becomes greater than R. Okay, either we have returned the mid that we have found, or my left is pointing to index that is now greater than my right, which means what? Which means either target. So target basically there must have been two situations. Either we were trying to look for the like the number in the next half, then we must have moved left to mid plus 1. Now it could have been a case where left is greater than right, or there must have been a case where right was placed mid minus 1 and now it's smaller than left. So those are the two situations where it's coming out. In both cases we know that left is now pointing to a position where the number target could be inserted. I think we have gone through it. I don't know what else I could say here that will prove it. So here we can just return left, and I'm sure you can play around with the logistics here and have like another variable that could store the value of a position that you can store from the mid only, since it decides over here and this also decides over here, so left will be mid plus 1. Okay, so that result could be saved here and that could be returned, but we don't have to have this extra variable to return. Okay, all right, so let's run it on the examples. Let's zoom out. Right, so I think LF unmatched, yeah. All right, let's submit. Awesome. Time complexity big of log n, and we have gone through that derivative where we found out why it is log n, and space complexity is big of 1, that is constant. Let's go to AlgoYogi and mark this solved, and see you guys later in the next problem. Until then, bye bye.